So far where we are is we started with two NOR gates. We put the two NOR gates together. We came up with a latch, SR latch. Then we said, well, we don't really like SR. We like to have a timing control first, and then we did the clocking. So we said that at least when S and R are taken, they are taken when we tell it to. So that was one improvement. The other improvement was we said we don't like SR, but then we like a data to be saved. So we put an inverter between S and R, and then called it a D-Latch, and the D-Latch is clocked. That means on the clock, the data will be latched into the output of the latch. So that's good. But then the problem with that is it only latches one bit. Okay? It's not a lot of information that is saved, and we may need more information to be saved. Okay, that's no big problem. We can put several of these together and make it a larger structure with more bits being saved. I'm going to show you that. But then there is another problem, and that is the problem of transparency. Okay, transparency always is not necessarily always good. Okay. And I'm going to talk about transparency now. And before that, I'm going to show you the for a larger memory structure. And then we talk about the transparency. So let's get into this. We are talking about what is referred to as master-slave flip-flop. Okay. That's the structure that removes transparency. When we get to that. Preparation for that. Let's talk about one bit saving more data. Instead of one bit, let's save more data. Well, put four of these together, and then this becomes a 4-bit register when you have all the control signals wired together. And instead of only one bit, you are saving 4 bits. That becomes a structure like this. This is the notation for it. The C1 means that this clock controls the one on the left-hand side. See, the here. The one on the right-hand side means that this is controlling. The one on the left-hand side means that it's controlled. That means D is controlled by the clock. When the clock is 1, D passes through. And then the clock being 1, D passes through. The notation, see the notation here. Okay. A pulse on the clock. That means this is a transparent register, a 4-bit transparent register. And the good thing about this is that it saves 4 pieces of information. Let me zoom on this and see. One on the right hand side means controlling, ing. One on the left hand side means controlled, ed. And then the pulse on the clock means the transparency, which means that when the clock is 1, the D passes through. Okay, it is controlled as such. But then at least the good thing is that it saves 4 bits, meaning that it has possibility of saving 16 different numbers. 0, 1, 2, 3, and so on. Let's, before we talk about the problem with this, let's write the very long description of it. And that is module. Let's call this one quad D-Latch. Okay. Input clock input 3:0 D in output reg 3 colon 0 q out always when D in changes, a bit of D in changes or clock changes, if clock equal one tick B1. Okay, I have to have equal, I have to have two equals. Let me go back and make sure that I have done that in the I'm going back to slide 8. That has to be two equals. All right. Yeah. This is sometimes missed. Yeah, I don't have a problem here. Anyway, I'm back to this, slide 13. And if clock equal to one tick B1, then Q out gets D in and module. Okay, that's all there is to it. This became a 4-bit latch, which we call it a register. The only thing about this is that all the latches have the same clock control, and therefore you're seeing that I'm only using one clock to clock in all 4 D-ins into Qs. All right. So we are so happy with this that we say, well, let's build something out of it. Okay. I like to build a counter. Okay, counter is this. Counter is an instrument, is a device that keeps a count of certain things. Okay, like a tally counter. You push it, and each time you push it, the count goes up. You push it again, the count goes up. Okay, now that I have a component, this thing here, that is a component that saves something, at least saves a 4-bit number, 16 different numbers it can save. I can build a counter, or I think I can build a counter out of it by saying, let's take the incrementer here, and let's take the 4 outputs, feed them back into the incrementer. Okay, these 4. And then let the incrementer add a 1 to whatever the input is and produce on the output. Okay, so if the incrementer is 1 0 1 0, which is 10 now, the input, if it is 1 0 1 0, it increments it, makes it what? Makes it 11, and which becomes, let me write this different color, becomes 1 0 1 1. Sits here, sits at the D input until what? Until clock arrives. As soon as clock arrives, the 1 0 1 1 11 clocks into the register. That means this goes here, this goes here, here, and here. So what I have here is 11. And then this 11 feeds back and comes and sits here at the input again. When it sits at the input, the incrementer increments it, and therefore what it has now is it has turned it into 12, which is 1, 1, 0, 0. 12 sits there. Okay, so remember I started with the contents of 10, okay, which was blue. 1, 0, 1, 0 became this. Now 11 is at the input. The incrementer adds a 1 to it, makes it 12. 12 sits at the input for the next clock. As soon as the next clock arrives, 12 passes through these latches, goes to the output, and therefore the output now becomes 1100. As soon as the output becomes 110, it goes back to the input. 110 goes back to the input of the incrementer. The incrementer again adds a 1 to it, and the result of adding a 1 to it becomes 1, 1, 0, 1, which is 13. The number 13 sits at the input, waits for the next clock. So far, remember, I have given it 2 clocks, going from 10 to 11 to 12. Okay? So that is... Okay, my first clock took me from 10, this was to 11. Okay. My first clock took me from 10 to 11. That's 1 clock. The second clock took me from 11 to 12. Now I'm giving it another clock. Okay? What I have at the input of the latches is 1011. As soon as I open it up and give it another clock, this 12 becomes 13. Okay? So perhaps I do have my tally counter. Each time I press on the input clock, which is this signal here, anytime I push on this, I get a count up until it reaches 1111. 1111 incremented by the incrementer becomes 0000, and therefore it rolls back to 0000 and then count up and count up again. Okay? So it works. Not really. Okay? Remember what I said about the transparency issue. Okay, the transparency issue says this. It says that if you take one of these latches, which I'm going to redraw here, okay, if I have one of these latches, when the clock becomes 1, okay, this input, the input on the right propagates here, okay, and propagates to the output, okay. That's the output from the incrementer, propagates to the output, and the clock is still 1. That output of this latch goes back, that output of the latch goes back to the incrementer circuit and then comes back here. There is no guarantee that by the time that output of the latch reaches back through the incrementer and reaches back into the input of the latch, there is no guarantee that my clock is off. My clock may be on again. Still. So what happens is I go from 10, my clock is on, to 11. 11 comes back, my clock is still on, goes to 12, goes to 13. It cycles several times before I close the clock. So what is happening is that I'm not getting one count up, I'm getting multiple counts up. So you might say, well, so why do you do this? Why don't you limit the clock duration so that only one count is done? That doesn't work because you don't really know the delays of the gates. And maybe even one bit has a longer delay than the other one. The logic for the incrementer may be different from one bit to the other one. And remember, if you are building the incrementer using half adders, the least significant bit has the smallest delay. Remember, an inverter is for the least significant bit, okay, between the input and the output, whereas the last one has all the accumulation of all the delays of the other bits. And therefore, there is no way I can say that I'm only going to let one bit to go, one count to go through, and I close the clock. Remember those tally counters when you press your finger on the push button there? What happens is, doesn't matter how long you keep your finger on the push button, as soon as you raise your finger, it counts once. Does not matter how long you hold your finger on the counter. Okay? But then my counter doesn't work that way. My counter has problem. Why does it have problem? Because of transparency. Because while the clock becomes 1, the latches are transparent. That means the input passes through to the output for as long as clock is 1. And that's the problem. That is the problem because the duration of the clock, the input goes to the output, goes back through the incrementer, goes back, goes to the latch again, goes back and back. You don't know how many times. So this is not something that I can use for a counter. I like a push button to be pressed, and when I release it, count up, regardless of the duration of the time that you are holding your finger on the push button. Okay? What do I do? I have to remove the transparency somehow. Look, these are the double doors that when you want to go inside the building, because of the air-conditioned inside of the building and the cold weather outside the building, what happens is you put double doors so that the person that wants to go inside the building, first the door on the outside is open. The person passes through, reaches the middle area. So there are 2 doors. Instead of 1 door, there are 2 doors. The door on the outside, this is out, this is in. The door on the outside closes. The person is sitting in the middle or standing in the middle. The door on the inside opens and the person moves out. And then for the next person, the door on the inside closes again. Okay, like this. And the door on the outside opens. And then the same thing. Okay? How did I manage this? You never have transparency from here to here. You don't have transparency. If you had 1 door, you would have transparency. What you created here are 2 inverting doors. Okay? means one opens, you go halfway in between, that closes, the other one opens. They are complementary to each other. The doors, one is invert of the other one. Then I say, well, why don't I do the same thing here? Instead of having one door that is causing that problematic, see, this is the transparency. Instead of having one door that is causing this problematic transparency during the clock, let's have two doors. And therefore you go halfway in between, and then the other half out. So what I want is a structure that is not transparent. Okay? What I want are two latches, one latch, second latch, that work opposite to each other. That means I have a latch, another latch, I have the data coming here, reaches the middle of the two latches, reaches the middle of the two latches, D, Q, and then next the data will go from the middle to the output. And therefore what I do is I take my clock input, connect it to the first latch, which I call it master, complement it, connect it to the second one, which is the slave. The data from the left-hand side first goes halfway from here to here when the clock is 1. Okay? See, when the clock is 1, the data goes halfway here. But then it just stays there. The reason it stays there is because this is 0. This other door, the second door, is not allowing my data to go anywhere beyond this middle point. And then what happens is clock now becomes 0. When clock becomes 0, the inverted output becomes 1. The door on the left-hand side closes, and my data that was sitting here, not being allowed to go forward, now goes forward to the output. Exactly as these doors are happening. Exactly as is happening in these doors. I removed the transparency. What I created is referred to as a flip-flop. Okay? When we talk about flip-flop, we are talking about a memory element that does not have transparency. Okay? So let's look at our D flip-flop here, and this is the structure of my D flip-flop. This is the slave, and this one is the master. Okay? When clock is 1, data goes halfway. When clock is 0, data goes the other half. There is absolutely no time that both of these are conducting. There is absolutely no time that the data goes all the way through, and no transparency here. Okay? Non-transparent D. We call this flip-flop. Now if I go back to my counter, instead of using only one, I use both of these. Okay. Now I have flip-flops here. What I'm going to do is I'm going to wire the clocks together. This is the push button. Okay. I'm going to connect my D inputs. This is bit number 0, 0, 1, 2, 3 to the incremental outputs. And then I'm taking the outputs from the flip-flops, from the D flip-flops, feeding back into the input of the incrementer. Each time I push a button, each time I press this push button there, my count only goes up one position. Okay. All right. We done a flip-flop the same way we did latches. We did the Verilog description. Now let's do the Verilog description for the flip-flop. This is a D-type flip-flop, or more accurately, it is a master-slave D-type flip-flop. We will see that there are other master-slaves, but for now, let's focus on the Verilog description of it. Okay. Let me go ahead and write module D flip-flop master slave. Input D CLK for the clock, output Q. Notice that I usually do only Q, and Q bar is just an assign, and just the complement of Q. Okay, so let's do reg Q. Okay, reg. My reg looks a little bit like REQ. All right. What I want to do is I don't want to learn something new yet. I want to do what I have done before, which is writing the two latches. See, I have a latch from here to here, and then I have a second latch from here to here. Let's write the first latch. I have a QM master, reg, Q master. Okay, always D, comma, D is the input, D, comma, CLK. Okay. If CLK Q master gets D. Okay. No begin or end needed. And then I'm gonna do, let me do this. Let's say wire CLK bar, and let's say assign CLK bar equal tilde clock. So this is CLK bar. And then I have another always statement. Now this one, the inputs are QM. Okay, yeah, it is QM instead of D. and then CLK bar instead of the clock. And then I say if CLK bar, then this one, Q, gets QM, which is the D input for the second flip-flop, and this is end module. Okay? That works. That works, but then I'm gonna do something a little bit better. See, let's start with this. Let's say this is my clock, and the clock is ticking, goes on, off. And remember how it works. When clock becomes 1, immediately, when clock becomes 1, the value of D is taken and goes in and sits in QM. Okay? And sits in QM. That sits there and doesn't go any further until my clock becomes 0, this area here. When clock becomes 0, the value that was sitting in QM now goes all the way to Q output. And therefore, the value of D was taken at this point, and then this is Q. I'm using uppercase Q, okay? This is Q. Q is not touched until clock becomes 0. When clock becomes 0, the value of D that was stored in QM actually transfers into Q, and in this case, Q becomes 0. Because there was a 0 here, that 0 that was captured when clock was 1 goes onto Q after clock becomes 0. Okay? Let's do a few more. Later on, my D becomes 1, stays 1 throughout this clock period. At this area here, the value of D, which is 1, gets captured into QM. It reaches into QM, and then Q is completely disconnected. When clock is 1, Q is completely disconnected. But then when the clock becomes 0, the value that was sitting in the middle of the flip-flop, the QM value, that one transfers into Q, and therefore right here, this becomes a 1. Okay, so let me show with two different colors. One color is blue when the clock becomes 0, and one color is red when the clock is 1. Actually, the only time that you see your Q changing is when clock is 1. The only time that you see your Q changes is when clock goes from 1 to 0. The only time that the D value is captured is when the clock goes from 0 to 1. Okay, so when the clock goes to 1, D is captured, sits there until the blue area when the clock becomes 0. So this continues on and on. Okay, so let me do a few more. Okay, here. When clock becomes 1 in this area here, the value of D is 0, and that value is captured in the middle point in the master, in the middle of the flip-flop. Nothing happens on Q. Okay, nothing happens on Q. Q is 1 now. Okay, until my clock goes from 1 to 0. When my clock goes from 1 to 0 in this area here, that's when the 0 that was captured in the middle of the two latches, that value transfers to my Q, and that value is 0. Okay, and therefore my Q becomes 0. because of this 0 that was there. Okay, this one. Later on, let me do another one here. This time, this is a 1. The 1 goes, sits in the middle. No change on Q. Okay, no change on Q. Q continues as it is until clock changes from 1 to 0. In this area, the second door opens. The second door sees at the input of the door what? A value 1. And therefore, the value 1 in this time here will be transferred into my output Q. Okay? Without going through all this analysis, this is something I'm going to look at. My output always changes. See, my output always changes after the falling edge of the clock. After my clock becomes 0, my output changes. What value does it change to? The value of D when the clock was 1. And therefore, here stays 1. Here, D is 0. And therefore, this changes to 0. And then remains 0. What I like to show here, what I like to have shown here is that my output changes only when the clock goes from 1 to 0. Okay? I'm going to write another description, making this real simple. Module, D, flip-flop, master, slave. I'm going to look at this more behaviorally than the left-hand side that I did the very log. Input, D, clock, output, reg, Q. Always. On the neg edge of the clock. On the neg edge of the clock, falling edge of the clock, the value of D goes into Q, and that's all there is to it. Q gets D. Okay? True that I have skipped a lot of details. I have skipped the fact that D goes halfway in the middle, and then from the middle it goes to the output. I've skipped the timing of all of this. Okay? But functionally, this is a perfect description of my master-slave D-type flip-flop. Corresponding to this circuit, this Verilog description, and the fact that if this is the clock, this is the D input, the value of D after the falling edge of the clock here appears on my Q output. So let's say Q is 0, and then right at this point Q becomes 1. Okay, which is this value of D, which is captured this value of D, which is captured when clock becomes 1, and the blue area is when the clock becomes 0. That's when the output is affected. So that's the timing, that's the circuit, that's the Verilog description. Let's, instead of drawing all of these, writing Verilog and showing that complex schematic diagram, let's do a symbol for this. The symbol is the following. C, 1, that means C is still controls. 1D, D is still the controlling. I'm sorry, the controlled. D is the controlled. C is the controlling. Q is the output. Okay? And then the output happens on after the falling edge of the clock. Falling edge of the clock. See here, this is the falling edge of the clock. And therefore, I describe this circuit by this notation. The triangle means edge. Okay? But then we have a negative edge. And therefore, I put a bubble here indicating this is negative edge. If it were positive edge, I would do just a triangle. So this is pos edge. This is neg edge. Okay? And this is the symbol for that. Let me do one last thing here. Remember we showed the controlling and controlled. This is controlling, this is controlled. And how does C control D? It controls D by this notation here, which is, in this case, neg edge. Okay? Which is this neg edge. All right. So in most cases, we'll be using this symbol to imply this description. All right, we're done.